So I know some of you asked 322, the coffee problem, had some questions on it. So I thought I'd quickly run through it. I think it's a great problem because it does connect what we've been doing with exponential functions to a real-world scenario, especially dealing with the concept of room temperature. So we know a couple things. The first thing we know is that the initial temperature of the coffee is 180 degrees. So if we thought of this as a data point, we think of it as 0 times 0, it's 180. And then we also know the temperature of the room is 70 degrees, is room temp. And then in part A, it says 5 minutes after Julie pours her coffee, the temperature is 160. So there's our second set of data, 160. And then we have to use that to predict the temperature for the coffee after 10 minutes. So 15 minutes after it was poured, 10 minutes after the 5. So using this data, these 2 points, and then using this information, which some of you I think had a hard time with, we're going to come up with an equation to solve. Alright, so let me go ahead and erase this. So this is going to be like this problem we did in class, the system, meaning we're going to have to use 2 equations here. The first one, we'll go ahead and write it out. This is your x and y, and this is your x and y. Again, we will think of this as y equals a times b to the x. I know it gives you m and t, but we'll use this form. So we can write this out as 160 equals a times b to the 5 over 180, which equals a times b to the 0. The one problem with this is this whole 70 degrees. Now if we think about what this graph is going to look like, if in fact it is following this trend and it's an exponential function, it won't be growing, it's going to be getting cooler, it's going to be decaying. So if we're going to graph this out, it starts at 180, so we start like 180 up here, and it's going to cool down until it gets close, and visually it helps if you see this. It's going to get closer and closer to room temperature, which is 70 degrees. Now if we look at this, it's not included in our equation right now, but it's in our graph, and this is your k-shift. So we're actually adding 70, we're shifting the graph up 70 units. It will not pass 70 because it's going to cool to that temperature. So the one part that wasn't included here was our plus k. And your k is going to be plus 70 on both of these, because that's your room temperature. Now, once we have that, we're going to want to take care of that 70. So you're going to want to subtract it from each side. So I write this. So we're going to do minus 70, and we're going to do it over here too. So this gives us 90 equals ab to the 5th over 110, which equals ab to the 0. Now we can go ahead and solve it for the appropriate temperatures. We're going to divide, the a's cancel. We get 9 over 11 equals b5. To take care of the b, we're either going to take it to the 5th root, or we can take it to the 1/5 power. That might be easier for us, 1/5. So b is equal to, this will cancel, 9/11 to the 1/5. Okay. Now the nice thing about this is we already know what our initial temp is, or A, which is going to be 0. So my A, not 0, excuse me, 180. 180 is my initial temperature, because that's where we're starting. So I know my A is equal to 180. Now with this with a and b, we can go ahead and write our equation. It'll be y equals 180, which is my initial temperature, times 9 over 11 to the 1/5 x power. And there's my final equation. From this, you can tell that this value here is less than 1. So since b is less than 1, we know I'm dealing with decay. And then, actually it won't be, yes, it'll be less than 1. And if you wanted to distribute that 1/5 in, you could do that too. I don't have a calculator in front of me, but this could also be written as y equals 180 times the 5th root 9 over 11 to the x. That could also work. Either way, radical form or fractional exponent. Alright, so I hope that helps with that one. Oh, and we can't forget about our shift of 70. So you need that 70 in there. Don't forget about the 70. I hope that helps.